So we are discussing about different factors. Suppose utilization factor, then depreciation factor, and their basic formulas. Okay, basic formulas for the depreciation factor and the flux, illuminating flux. Okay, and some very two examples were discussed in last class. Okay, where we are going to calculate that utilization factors and other factors, or if it is available, then we are calculating the number of lamps are required for our application. So another problem you can see. Okay, so another example. Okay, so find what was that example. You please note it down in your copy. Okay, find the total saving of electrical loads. Okay, total saving of electrical loads and percentage increase in the illuminations if instead of using 12, okay, 12 150 watt tungsten filament lamps. Okay, it is given individual is 150 watts. So 12 tungsten filament lamps total loads, how much it is coming? It is 12 into 150. Okay, so it is coming near about 1800 watt. Okay, we use the 1280 watt fluorescent tube. Okay, so one is 80 watt, another one that 12s are there, so you can also multiply that 12. Okay, and if maybe assume that there is a choke loss 25% of the rated lamp voltage. Okay, so it is 80 watts, so 25% has lost for that. So how much total watt was there? Okay, so total load of the tube, that is 80. Okay, 80 watt plus that wastage is there. Okay, due to choke loss, so that is 0.25 into 80. Okay, and average illumination efficiency, okay, throughout the lamp is 15 lumen per watt. For each tube 40 lumen per watt, and the coefficient of utilization remain the same both the cases. Okay, so we have to calculate them. That's given that 12 lamps are there, sorry, fluorescent tubes are there. Okay, so 12, so you can calculate 1200 watt. Okay, so now net load saving means what happened. So sometimes you are considering, so load saving means you are just reduce them. So how much changes are there? 600 watts. So A is the room area and eta is the coefficient of utilization or utilization factor. So you know the formula of E into A equal to 12 into 150. Okay, into 15 into n. Okay, so 1 for 15 into n, so directly it is coming. So how much values are there? So you are getting the value of illumination of lamps U1 equal to 27,000 in per area lumen per meter square. Similarly, you are also getting the illuminations of the tube, that is your E2. Okay, so you can so which one is your lamp? It was 27,000 and tube it is more 38,000 neta. Okay, so in per A. So both the cases you can see that values are so if you directly getting that percentage. Okay, so n by a will be everywhere as well as numerator and the denominator, so they can cancel each other. Finally, you will get that 42% increase of the illuminations. Okay, simple mathematics. Okay, next problem, what you are able to see. So you can also take it, you can note it down to your copy. So what is given? So that a hall. Okay, so drawing hall is given for an engineering college to be provided with the lighting installations. Okay, so installation is the lighting installation. The hall is size of that hall is 30 meter into 20 meter into 8 meter height. Okay, so 30 into 20 into height is 8 meter. And I think the separation of two lamp is 5 meters. So it is 30 meter, it is 20 meter. Okay, and 5 meters are there. Okay, all of you please cross check it. Any mistake is there, please let me know. Okay. So 30 into 20 into 8 meter, that height is given. Then mounting height is mounting height of the lamp you can consider, that is 5 meter. Okay, so 5 meter, and the required level of illumination is 144 lumen per meter square. That's given. Okay, so required level of illumination 140 lumen per meter square. Using the metal filament lamp, okay, metal filament lamp is there. Estimating the size and the number of the single lamp luminaries, and also draw their specific layouts. Okay, so layouts are given, utilization coefficient given, or utilization factor is 0.6, maintenance factor or the depreciation factor is given 0.5, space per height ratio is 1. Lumen per watts, okay, so lumen per watt is 300 watt for the lamp, okay. So, and sorry, 300 watt lamp is 13 lumen per watt for 300 watt lamp, and lumens per hour for 500 watt lamp it is 16. Okay, so lumen per watt is 16 for 500 watt lamp and 13 for 300 watt lamp. Now solution is there, flux you have to calculate. You know that formula, that phi is, you already mentioned, E A whole divided N into P. So all those values are already given. Area is there for 30 into 20. Okay, so E also given for how much value of E area. E is given that 144 lumen per meter square. Here you can see that E. Okay, so E is already there, 144. Then depreciation factor for 300. Sorry, utilization factor for utilization factor is given 0.6. Okay, and then maintenance factor is 0.75. Okay, that's given. So 192,000 lumen is coming. Okay, so for then lumen per watt for 300 lamp is 13. So lumen per watts. Okay, so 500 lamp. Okay, so it is how lumen output is given. Okay, so lumen per watt for 300 lamp is 13. Okay, so that 13 and 500 watt is 16. So what will be the number of lumens per watt is 500 watt. Okay, so directly we are getting how many values, that is 15 into 500 into 16, it is 8,000. Okay, so number of 500 watt lamps required, you can totally divide it, the total lumens whole divided by. So 16 is, this is for 1. Okay, so 16, yeah, so total 16 lamps. This is 13 lamps, this is 16 lamps. Okay, 16 into 500 or 13 into 300. So both the cases, if you multiply them, so you'll get one case, it is 3,900. So 3,900. So it is coming 3,900. Okay, another one is, if you multiply them, it is 8,000. Okay, so if you divide all those factors, so it is coming 24 and 49. 24 for your 500 watt and 49 for your 300 watt numbers. Okay, so now what you can do, so 300 watt cannot be used because the number cannot arrange in all 30 meter into 20 meter. Why? Okay, so space per height ratio of unity. Okay, space per height ratio unit. So 500 watt lamp in the 4 rows. Okay, so it should be, the number should be arranged such a manner. Okay, so that should be calculated, 4 rows and 6 lamps. Okay, so 6 into 4, it is 24. Okay, so 4 rows and 6 lamps per here, but it is 49. So you can cross check it. It is it's not coming perfect manner. Okay, so each of the spacing, as spacing is given 5. Okay, spacing is already there 5. Okay, so it should be accommodated. Okay, proper manner. Spacing is 5, both width and the length of the halls shown in the figure. So directly that figure you can understand. Okay, simple, nothing complicated, very simple problem. And at the time of exam, similar type of problem will be come. Okay, so please prepare in your home and solve it. Okay, so next problem, what we can see over there. So it is given that a figure is given. Okay, so estimated. Okay, so you have to ask for the estimate, the number and wattage of lamps. Okay, number and wattage of lamps which would be required to illuminate a workshop space. Workshop space is given 15 meters. Okay, 16 to 15 meters. by means the lamp mounted 5 meters above of the working plane. Okay, so 5 meter above, the average illuminations required is about 100 lux. Okay, so 100 lux average illumination. So coefficient of illumination is 0.4. Okay, so utilization factor is 0.4. Luminous efficiency is 16 lumen per watt. That is given. Okay, so assume a space per height ratio of unity and a candle power depreciation of 20%. Okay, 20%. So I hope you can understand. Okay, so that's given. So all of you try to calculate it in your copy. So phi you need to calculate. E is already given. That is 15 meter. 15 into 60. 60 into 15. Okay, E is there. 16 into, sorry, A is 16 into 15. E is there 100 lux. Okay, that is your 100. And efficiency factors is given. Okay, so 0.4. And efficiency you need to calculate the 20% depreciations. Okay, so that is 1 by 1.2. Okay, so 1 by 1.2 directly coming. Okay, so height per ratio is given unity and the candle power is 20%. So unity, so that spacing is it is 1, height is 20% of the depreciation, so 1.2. Okay, so that's why the ratio is coming 1 by 1.2. Okay, directly we will get that lumens, that is 25 to 10 to the 4 lumens are there. Now what is given? So wattage required, how much watts are required? So total you are getting that value, luminous flux. Okay, flux is there, that 24/7 into. So now we are divided by 16. Okay, so that's luminous efficiency is given 16 lumen per watt. Okay, so it is 27 into 10 to the 4 lumen. So how much watt is required? Okay, so you have to for one. So directly you will get that value divided by 16. Okay, 16 is given, that luminous efficiency. So 17,000 watt you are getting. Okay, for a space per height ratio of unity, only 3 lamps can be mounted along the width of the room. Similarly, 12 lamps can be arranged along the length of the room. The total number of lamps, how much values are there? So require 12 into 3, that is 36. Okay, you have to calculate it. Okay, how many numbers accommodate? Okay, so you can calculate, it is coming 36. So similarly, 12 lamps spacing is 5. So 5 divided by 60, how many lamps can be there? 12 lamp can be there. Okay, 60 by 5. Another thing, that 15, okay, 15 meter and divided by 5 meters, so 3. So how many numbers? 3. Okay, 3 rows maximum you can accommodate. So another 12 column. So 12 into 3, that is 36 lamps will be there. For previous one also same. Okay, that is 30 divided by 5, that is 6. 20 divided by 5, that is 4. 6 into 4, 24 previously. That exactly match. Here the same thing, 36. Okay, so total number of lamp can be, maximum number of lamp is 36. Now total wattage is there, 17,000 watt. Okay, so for individually how much? 17,000 whole divided by 36. So individual lamp should be 472 watt. We'll take the nearest standing lamp of 500 watt. So standard. Okay, so standard lamps is 500 watt. Okay, so 36 lamp will be arranged as given in the figure. Okay. So you know the standard resistance. So whatever mathematical value we are getting, okay, nearer standard value means suppose we are getting some fractional value, but it's not possible for the fraction value of lamp. So we have to consider some integer value. Okay, round up figure, that is number one. Then what you need to see, that round up figure, that value may be available in your market, may not be. Okay, maybe means if that value is exactly same as the standard value, then it can be available in the market. If it is not exactly same, so you have to find out the nearest standard value, and that standard value you can accommodate here. Okay, and you can recalculate it, but more changes will not be observed. Okay, so you please, that's your one assignment. Okay, when you are solving that numerical problems, okay, in any of the standard book to your copy, and you please take that screenshot of this question. Okay, so all of you please try to solve this question paper. Okay, so 5 problems are there. You can consider it is an assignment type thing. Okay, so all the numerical problems will be collected as an assignment. Okay, that I'll ask you when you need to submit it. Okay. Do you take the screenshot?
Yes, sir.
Yes, sir. Good, good.
Yes, sir.
Okay. Okay, so now we're talking about that floodlighting. So, okay, so you know that cricket match, okay, or any big space. Okay, so you want to suppose any occasion is going on. Okay, so we are going to arrange that flood lighting. Why it is flood lighting? You know that floods of light. Okay, flooding of light, like that it is flood. Okay, the means of flooding that large surface. Okay, with the help of light from powerful projectors. Okay, the flooding is employed for the following purposes. Okay, so what are the following purposes? Number one, for aesthetic purpose, as the enhancing and the beauty of the building by the night. That means flooding light ancient monuments. Okay, religious building or that important festival occasions. Okay, for advertising purpose, flooding light, huge hoardings, commercial building. All are the examples of the flooding light. So for industrial and commercial purposes, as in the case of railway yards, sports stadium, quarters. Okay, so that flood lightings are normally there. Okay, so you can see for the flood lighting that projectors, that option is there, that projector option. Okay, so you are giving that, you can see the area of lighting. This is your area of lighting. Okay, so first it can be projected such a manner. Okay, so holograms, okay, whatever so there, so you can project that lighting. Okay, diffractions. Okay, last class I made some missing. I told in case of diffraction, instead of diffraction I'm telling diffusions. Okay, so it should be diffractions. Okay, not diffusions. Diffusions is another thing. Okay, so that is also related to the physics. Okay, I have mixed it up. Okay, and that solutions, diffusion is related to that solution chapter, and diffractions is related to our light chapters, particle nature of lights. Okay, so by mistake in my last class, I some of the time I have told that diffusions. Okay, that is not diffusions, it should be the diffractions. Okay, so here you can see that usually that floodlight projectors having the suitable reflectors. Okay, reflectors means you can see that projecting. Okay, so concentrating that portions. Filter standard is 250, 500 or 1000 watt. Gas filled tungsten lamps employed. One to typical floodlight installations are given in the figures that keep 15 meter to 30 meter away from the surface, 15 to 30 meters. Okay, and provide the approximately and parallel having that 25° to 30°. So you can see sometimes angular version is there here, 25 to 30°. Okay, shows in case when the projectors cannot be located away from the building. In that case, an asymptotic reflectors is used which directs more intense light towards the top of the building. Okay, the total luminous flux required to floodlight a building can be found that phi equal to EA divided by neta into P. Okay, so phi means flux is already there. However, in case of flooding light, okay, flood lighting, one more factor to be taken into account. That factor is known as the waste light factor. Okay, so it's not like that whatever lights you are given, all the light will be projected at the space. Some of the light also be there here and then it will be moving. So you are not getting it directly. So some of the portions of the light may be wasted. Okay, it is so because when the several projectors are used, there is a bound to be certain amount of overlap. Okay, certain number of overlap, and also because some light would fall beyond the edges of the area. Okay, beyond the edges of the area. So that is your edge. Okay, beyond the edges of the area. Okay, to be illuminated. These two factors are also taken into the account by multiplying the theoretical value of the flux required by the waste light factor. Okay, so you have to calculate that waste light factor. So additional point in simple manner, one factor is multiplying with that one. So that is W. So exactly whatever flux you are projecting here, you are not getting. As simple as it. Okay, so how do you replicate it? So one additional multiplying factor you are adding, that is W. Okay, that is called waste factor. That value is considering nearer to 1.2. Okay, for regular surface and about 1.5 for the irregular surface. The objects or states means based on that one. So which portion will be wasted? Okay, the formula of the calculating the simple thing. So phi initially it was EA whole divided by neta into p. So now it is there phi equal to EA W whole divided by neta into p. So only W is your waste factor, that coming additional thing. Okay, so diffractions. Okay, so here you can see, well, you can understand that waste factor, that points are there converging, or at that point is concentrating other lights. Are you getting my points? Means some of the portions you can see the common portions. Okay, covered by the four lights. Okay, common portion is covered by the four lights. Okay, you can say like that you are not able to use that light. Okay, so from the example, what we can see, it is desired to floodlight. Okay, the front of the building is 42-meter wide. Okay, so it's given. So 42-meter wide. Okay, and 16-meter height. 42-meter wide and 16-meter height building. It's given. Projector is 30-degree beam spreaded. Okay, and 1000-watt lamp giving 20 lumen per watt are available. Okay. So 30-degree inclines are there. Here you can see 30-degree, both the cases, 30-degree inclines. The projectors are there. Okay, it's normal conditions. So 42-meter wide and 16-meter height. Okay. So now what you need to do, if the desired level of illumination is 75 lumen per meter square, if the projector are also located ground level 15-meter away, so sorry 17-meter away, design and show a suitable scheme. Assume the following. So given coefficient of utilization, so it is given 0.4 or utilization factor. Okay, that is 0.4, depreciation factor 1.2, waste factor is 1.2. Okay, so you know the formula phi. Okay, phi equal to EA. So everything's are mostly given, that E is given 72. Here you can see lumen per meter square, that illuminations, level of illuminations, desired level of E. A you can multiply that value 12 into 16, that area. 42 into 16, that area, multiply that value, that is 672 meters square. W waste factor is given 1.2, N that is 0.4, and P is given that height per space by height. So that is given 1 by 1.3, that depreciation factor. Okay, 1 by 1.3, that is given. Okay, so and you are able to calculate the phi. Okay, so now phi value is coming. Please cross check that value. Okay, so if it is coming wrong, please let me know. Okay, so all values are given directly, we are replacing them directly. Okay, so here we are getting that height. So lumen output for 1000-watt lamp. Okay, so 20 lumen per watts are there, 1000 watt. So total power, total 1000 watt, na? So total lumen output 20 into 1000. So that is 20 into 1000 lumen. Watt can be cancel each other. Okay, so 20 into 1000 lumen. So we will get that value 20,000 lumen. Okay, and your total lumen flux is there 19,000. Sorry. 1,96,500 lumen. Okay, and you are getting that for each 1000 watt lamp, you are getting 20,000 lumen. So you can divide total lumen by in lumen per individual lamp. So it is coming nearer to 10 approximately. So we are getting some you are getting some fraction. So but round up that one that I am telling. Okay, so round up, if you do the round up, it approximately 10 is coming. Okay, so if 10 is there, so with a beam spread of 30°, okay, so it is possible to cover the whole length. Okay, so 30°, that's is possible to cover the whole length and the width of the building by arranging the 10 projectors. Okay, so how many projectors are there? 10 projectors are required in two rows showing in the figure. So projectors, you can see 30°. Okay, and projectors are connected such a manner so entire portions can be illuminated. Okay, so and that is given here. Okay, from that figure. I hope you are able to understand. Okay, so how it will be look like that diagram. So okay. Now different sources of light. Okay, so different sources of light means uh, so now we are discussing about different sources of light. So what are the different sources of light? Normally, you know that sun is the sources of light, but the rest of the thing we are converting that other energy to the light energy. Suppose electrical energy to the light energy. Okay, so we can say like that. All are the source of the artificial source of light. Okay, so different methods are there for producing that electrical energy to light energy. Okay, so based on the changes, based on the changing of their generations, okay, based on the changing of their generations, gradually, gradually that has been changed. Okay, so you know that initially we are using that. We are using that incandescent lamp. Okay, then you can understand that lot of losses are there. For reducing the loss, what we are doing, we are making that using some material which having negative temperature coefficient. Suppose you can consider just for an example carbon filament lamp. Okay, but you can understand that is not so much cost efficient compared to your incandescent lamp. So carbon filament lamp means their temperature is increased, I square RT, so automatically resistivity is decreased. Okay, so losses may be reduced, but cost per unit item is not so much convenient for the common person. Okay, so that's why what gradually we are switched to the next generations of lamps. Then in the market that fluorescent lamps will be there. Okay, so fluorescent lamp means you can understand both the electrodes will be there, and you are having choke current. Huge potential differences are there that may be responsible for breaking down that low pressure Okay, low pressure vacuum tube. Okay, that in between two electrodes. Okay, so there is a, after some times, due to that high potential difference, that that medium can be broken down. Okay, can be broken down, and there will be chances for the flow of electron. After flowing of the electrons, that may be responsible for the flowing of current in the reverse directions. That is the concept of the fluorescent lamp. But as I am telling, there is the inductor, and you can understand how much enable losses will be there. And as it will be in bulky nature, a lot of coiling will be there. Okay, so what we are doing after that, we are using the CFL. Okay, so compressed fluorescent lamp. So how do you make it compressed? Okay, that we are replacing that entire circuit. Okay, that entire circuit means that choke coils and the starter circuit. Okay, by the ballast circuit. Okay, so ballast circuit is nothing but a high circuit. Okay, so if it is working in high frequency, so automatically that amount of inductance you will get means XL. Okay, so inductive reactance. We are bothered about the inductive reactance. Okay, so that frequency is increased, so inductive reactance also increase without changing of that inductor. Inductor value may not be changed, but inductive reactance can be changed by changes of that frequency, inductive reactance and that starter windings. Okay, so high frequencies circuits we are using for, it's known as the ballast circuit for turning on that CFL. The rating also gradually decreased. First, initially that you know that in fluorescent lamp it was normal for our normal domestic purpose. Okay, that was minimum requirement was 60 watt, 10 watt. Okay, sorry, 60 watt, 100 watt, 200 watt. Okay, so you can also able to calculate that how much number of watt hour. Okay, so based on that you are considering that unit. Okay, so unit and the unit pricing, so your consumer tariff. Okay, it's your consumer tariff also been varying by using all those kinds of high energy demanding technology. Okay, so that's why what happened, you want to try, you want to that next generation lamp, they want to minimize the cost as well as minimize the loss. First concept was that minimize the loss. Okay, then minimize the cost. Okay, then you can make a comparison. It's not like that, both are in, there is a trade-off between minimizing of loss and minimizing of the cost. Okay, so inversely proportional, so you have to balance them and fix up a value where both you will also be gainer, and as your loss also can be in the form of cost efficiency and your electrical efficiency. Both the cases, basically cost efficiency means losses is more, means that price also you have to bear. Okay, so both trade-offs are required. Okay, both the cases the trade-off is required. Okay, so so that thing you can be remember, yeah, that thing can be calculated. Okay, so what we are doing, that ballast circuit is there, high frequency circuit for turning on that turning on those component. Okay, turning on that lamps. Okay, after that what we are doing then, CFL, then we are just changes to the LED lamp. Okay, LED lamp means their wattage is again still less. Okay, so fluorescent lamp was, tungsten lamp was minimum 100 watt. Now fluorescent lamp is coming around, gradually decreasing from 60 watt then 40 watt. Now after that we are also getting that's a 20 watt. Now you can get that LED, that CFL. CFL also be more or less 15 to 20 watt. Okay, and right now we are also getting that LED lamp. Okay, that is also minimum 10 watts. Okay, it's not like that more than 10 watts also available, but they are in costly. Okay, as their demand is less. Okay, so we are getting that one. Okay, so by that way the generation has changed. Okay, so that's all are the sources of artificial lamps. Okay, and why it is changing, the temperature and the efficiency. Okay. Okay, so the different methods of producing light by electricity may. Okay, so it's given the different methods producing light of the electric may. The board cells can be delivered into three groups. Okay, by temperature incandescence based on that, which depends. So when you are designing them, so it depends which how it will be considered. Okay, so in this method, the electric current is passed through a filament of thin wire placed in a vacuum or the inert gas. Okay, why that vacuum is not used? Instead of vacuum, we are using inert gas. So otherwise, that will be vaporized. Okay, that incandescent lamp, that material can be vaporized. That's why inert gas will be there. So in that earth, it is not possible to make that place vacuum. So that place must be. Hello. I'm in a class. You call me later, okay? Huh. So that's why that inert gas, it can be filled by the inert gas. Okay, the current generate enough heat to raise up the temperature filament of illuminous. Okay, the incandescent tungsten filament lamps are examples. Okay, tungsten filament lamps, and that's the temperature radiators. You can also see the temperature radiator. So that not like only electrical energy converted to light energy as well as heat energy. Okay, that's why the system is very lossy system. Okay, so it's not the cost effective system. By establishing an arc between two carbon electrodes, okay, electrodes, the source of light and in their case is the incandescent electrodes. Okay, the discharge lamp also be there. Okay, in this lamp the gas or vapor, the gas or vapor. হ্যালো, হ্যাঁ আমি ফোন করছি, আমি ক্লাসে আছি। হুম। Okay, so this lamp, so gas and vapor made luminous. Okay, discharge lamp means what happened? Instead of coil, okay, instead of coil, you are using some gas or vapor. Okay, that is going to illuminate it. So physically, no conductors are there. Okay, so you are using that the conductive medium through the discharge gas. Okay, suppose if you are using sodium vapor, okay, it will be in yellowish. Suppose you are using mercury vapor, so that also in some other color, maybe white. Okay, there is a not like a white. Okay, there is some gradations are there. Okay, so different colors. Sometimes it can be orange. Okay, so depends. Okay, it depends what type of things you are using. Yellowish sometime. Okay, so low pressure, high pressure. Based on the pressure, that colors also will depends. Okay, so that's come in gradually. Okay, I think in next class we will discuss about it. So different vapor slab, so that's better. So today we are not able to complete the entire thing. So next our next class is on Friday. Okay, I'll complete that discharge lab, so that portion will be completed. And suggestions and advice to my dear student that please solve all type of numerical problems. Okay, first complete it for tractions, then illuminations. Okay, from any of the standard book. Okay, we need to know the pattern. Okay, at the time of exam, that if you practice different numerical problem, okay, so you'll get the pattern may be match. Then data may be different. You can solve it. Okay, and it's a informative and very scoring subjects. Okay, please practice it in your home. Or I think now you will be in our institute. Okay, so we will meet soon. Okay, we will meet very soon. if the class will be going to conduct in physical mode, so we'll be meet very soon. Okay, so I'm expecting all those days. Okay, I will be meet very soon. So by the meantime, you please complete all those things. Okay, that illuminations and tractions, all the numerical problems, please complete it and practice it in your home or in your hostel. Okay, so I'm asking for that submissions. Okay, so and be prepared for that offline submission. If that classes will be there, so we can get it for offline submission also, and offline and online if possible online submissions. Okay, so in next class we can complete that portions. Okay, so discharge lamps. What are the examples of the discharge lamp? I'm giving mercury vapor lamps, sodium vapor lamps, neon gas lamp, fluorescent lamps. Based on that discharge, okay, the color also been different. Basically, there is a sedimentation of different chemical compositions. Your tube. Okay, so tube surface. So different compositions can be sedimented. So what happen if that electron is hitting there, so it can change its physical property, not the chemical property. Okay, and the color can be changed based on the options. Okay, so directly lights is based on the discharge through the gas and vapors, so not depends on the temperature. Okay, and for the high efficiencies. Okay, so discharge lamp and illumination light lamps all are there. Okay, so candle power emitted depends on the nature of the gas and vapor only. Okay, very simple thing. Okay, so we can complete today's session here. Okay, so next class we will discuss about uh, next class we can discuss about different types of lamp and their examples.